Okay, so this is part two. We're talking about irrational numbers. What is an irrational number? It is a real number. First of all, it has to be a number that is not rational. So here's a question. Is this number, well, is this a rational number? Is this an irrational number? Or is this neither? This is a question that shows up on quizzes and exams. Sometimes it's 1 over 0, maybe it's the square root of 2 over 0. And you might say, well, that's irrational divided by rational. Shouldn't that be irrational? But these are not real numbers. We can't divide by 0. So be on the lookout for that. It might show up in the homework or on a quiz. So anything with 0 in the denominator is not even a number. So it can't be rational, it can't be irrational. And keep this in mind that rational numbers can be written as decimals. However, their decimal forms never repeat and never end. So we've answered questions 1 and 2. Now we are going to try to find an irrational number between 4.2 and 4.21. Okay, so I suppose you could be clever and come up with some multiple of the square root of 2. But I want you to be able to find a decimal form. So, can we find a decimal form of an irrational number between 4.2 and 4.21? Well, like we did with rational numbers, it helps to add some zeros. Now I can see that these numbers actually are quite far apart. And now I need a decimal that never repeats and goes on forever. So I'm going to have to be clever. And there's a couple of tricks. Here is one of my favorite. What about 4.20010001, etc.? Now, this is a pattern. I know what comes next. After this digit here, this 1, there's going to be 5 zeros, then a 1, then 6 zeros, then a 1. So that means it will never repeat. Also, very important to include is the dot, 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 the ellipsis. This means it goes on forever. So both parts are very important. Now, just like with rational numbers, there's infinitely many irrational numbers in here. So let's find another one. Let's say here's 4.2. Here's 4.21. We add a 0, add 2 zeros here. Here's another way to come up with an irrational number that clearly never repeats and clearly goes on forever. Let's see if you can follow what this is doing. Do you see what I'm doing? These are the natural numbers as the digits. How do I know this won't repeat? Well, think of it this way. Eventually we're going to get to 100. So I'll have a 1 with 2 zeros. And then I'll get to 1,000 and I'll have a 1 with 3 zeros. And then I'll get to 10,000, have a 1 with 4 zeros. So it never repeats. And this tells me it never ends. Okay, there's many different other ways to do this, and you can get creative, but I mean, you could just use the even numbers. The thing is, you have to come up with a pattern that I can understand. So you need a pattern that never repeats. I had somebody once who did this. Let's see. Do you recognize this pattern? What am I writing down here? Whoops, I messed up. 8 plus 13 is 21. 34, 55, 89, 144, and so on. So I use the Fibonacci sequence. That's perfectly good. So if you like the zeros, use that. It doesn't have to be the number 1. You could write 4.205. 05. Nope, 005 is what I meant. You have to increase the number of zeros and make sure that I understand your pattern. Now, I'm going to give you an example of something not to do. Sometimes people start off correctly by adding a 0 and then they just go 4.2011355, some kind of just writing down some digits and then put a dot 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 on there. Well, I don't know what this is. I don't know if this is a rational number or an irrational number because I can't tell that it doesn't repeat. So this is we don't know. Let's just say that. This would be an incorrect answer because we don't know. We can't tell clearly if it repeats or not. It goes on forever. So don't do this. Do not do this. Okay, here's a challenge. Find two positive irrational numbers whose sum is rational. We have to have positive irrational numbers, so that makes this a little challenging. If this was not there, we could just use the square root of 2 plus the negative square root of 2 and get 0. But this is not positive. So how am I going to create two positive irrational numbers? Well, let's look at this. We know the square root of 2 is approximately 1.14 or something. Let me check it for us real quick so I don't say a lie. 1.414. Now, so I'm going to use the square root of 2 and form two irrational numbers. That's irrational because this is rational plus irrational. And my second number is going to be, we're going to add this to 3 minus the square root of 2, which is also irrational because this is rational minus irrational. So these are my two numbers, 3 plus the square root of 2 and 3 minus the square root of 2. And when we add them, we can get rid of these parentheses. And this equals 6 because the irrational numbers got canceled. And that is rational because you can write 6 as 6 over 1. So you could use another number. Let's do some more examples before we do this one. Maybe we could use pi. Pi is about 3.14. So I could say, how about 5 plus pi plus 5 minus pi. These are both irrational numbers. Why? Because they're rational plus irrational and rational minus irrational. But when we add them, we get 5 plus pi plus 5 minus pi, which again, the irrational part cancels and gives us the number 10. So there are many ways to do this, but make sure you get a positive irrational number. So now let's look at the next question. Number 5. Find two positive irrational numbers whose product is rational. Well, it turns out that this number here, these two numbers here, will work for multiplication. So let's try them and see what happens. So we have 3 plus the square root of 2 times 3 minus the square root of 2. And this is something you might recognize from algebra, that these are conjugate pairs. And this is how we rationalize denominators when we need to, by multiplying by the conjugate. So let's just be really careful and use FOIL and see what happens. So first, that's 3 times 3, that is 9. Outer, that's 3 times the negative of square root of 2, so that would be minus 3 root 2. Inner, that's 3 times the positive square root of 2. And last, what is last going to be? That is the square root of 2 times the negative square root of 2. Now, I can see that these cancel each other out. So I have 9, and I need to figure out what happens here. Well, it turns out you can bring that minus sign outside the parentheses, and then we're looking at the square root of 2 times the square root of 2, which by definition is 2. So this equals negative 2. So my final answer is 7. Is that a rational number? Yes, because it can be written as 7 over 1. Now, some of you may have realized that there's something easier we can do. It didn't say that the two numbers had to be different. What about the square root of 2 times the square root of 2? Well, that equals 2, and 2 is rational. And these are both positive. They're greater than 0. So that's sort of an easier way to do it. If they had to be different, you would want to go with this route. If they didn't have to be different, you could do this. Now, these two numbers over here, when you multiply them together, what's going to happen? Well, why don't we look at that? If we take 5 plus pi and multiply it times 5 minus pi, this is irrational times irrational. Remember, we can't always predict the outcome. We have to look at it on a case-by-case basis. So this time, if we do FOIL, something different is going to happen. First is 25. Outer would be negative 5 pi. Inner is positive 5 pi. And that looks promising. But what about the last? The last is pi times negative pi, and that's just minus pi squared. So I do get some cancellation, but I end up with 25 minus pi squared. And this is not rational. See, pi is a different kind of irrational number. Pi times pi is irrational. Square root of 3 times square root of 3 equals 3, which is rational. So, interesting properties of the irrational numbers. Okay, let's look at these and decide which of these numbers are rational and irrational. This is an irrational number plus a rational number, so this one is irrational. You with me? We could write it this way. It's the same number. Okay, what do you think about B? Do you remember that we showed that this is equal to the number 1? So this is rational. Right, let's look at C. This is an integer. Call it A over B, and B does not equal 0. So this is rational. Now look carefully at D. It's 1.01001. Then there's 3 zeros. Then there's 4 zeros. This number has a decimal form that never ends and never repeats. This is irrational. Square root of 17. 17 is not a perfect square. So this is also irrational. Now, let's look at F. F is the square root of 144 over the square root of 64. Well, square root of 144 is 12. Square root of 64 is 8. This is a rational number. And you could reduce it, but we don't need to. We're just answering the question. All right. Now, This is a question that you don't know the answer to, but I'm going to tell you, unless you've read the book. If we could pick a real number at random, if maybe we had this box that contained all the real numbers in there, all the real numbers are in there, and you could put your hand in and grab one, and out comes this number. And then you open up your hand and you look at it. What's the probability that the number you picked is rational? It is basically impossible to pick a real rational number at random. Now, the way we describe this um, in the book is they imagine, okay, suppose you're going to build an irrational number. And what you're going to do is you're going to use a six-sided die, or actually we would want a 10-sided die. So it has digits 0, 1, 2, 3, all the way up to 9. And you're going to build this irrational number by rolling the die. So maybe you roll a 1, then you roll a 3, then you roll another 3, then you roll a 5, then you roll a 9. And if you could imagine doing this, you get these numbers, and you keep doing this forever. Now, this is what we call a thought experiment because, of course, you can't do it, but you can imagine it being done. So imagine that you continue this process forever. If this number was going to be rational, it would have to repeat. So think about that for a minute. It would have to repeat to be rational. Well, that means at some point you're throwing the die and it's going in a pattern. You're getting the same numbers every single time, and that is impossible. So it's kind of a strange concept, but it's important. Why is it important? Well, if the probability that you can pick a rational number at random is 0, and we have this box of all the real numbers here, and when you pick a number, you go in there and you pick one, it's always irrational. What does that tell you about the size of the set of irrational numbers compared to the size of the set of rational numbers? Well, if you think about it for a little bit, here's just a sort of slang way to say it. There are way more irrational numbers than rational. Now that is a strange concept because you have these real numbers and they're made up of the set of rational numbers together with the set of irrational numbers. And there's no overlap. Now, if you look at the natural numbers, you could divide them up into the even plus odd. If you had a box of natural numbers and you pick one at random, the probability of getting an even number is what? It is 1/2, because half of the natural numbers are even and half of the natural numbers are odd. But with the real numbers, the probability that you pick one of these, a rational versus an irrational, you will always get an irrational, because there's so much more. There are way, way more irrational numbers than rational. And this is a concept that we will be talking about in chapter 3. And this is talking about the sizes of infinity. Yes, I said sizes of infinity. And it's a fascinating topic that, to me, and I hope it will be at least interesting to you. Okay, next, before you can do your next homework, you need to watch the next lecture on geometric sums, because the homework combines both topics. Okay, bye for now.